In today's video, I will be showing the difference between manual bolt hole scanning using a handheld manual probe like this versus semi-automated scanning with an Olympus Mini-Mite rotating scanner. There you got the probe inserted in the end. And the tester I'm using for the manual scanning happens to be my favorite tester, the Stavely Nortec Workstation 2000. It's just a real nice machine for making videos. I do all my research on this tester. And yeah, I like it. So let's get started. All right, again, this is the manual bolt hole probe. And we're just going to go through the setup from soup to nuts so you can see how everything is done. I really need, ideally, 3 different standards to calibrate for this, unless you have one that's got all of the necessary items in it. But for setting liftoff and just checking, if the probe's functioning, I'll just use an aluminum EDM block with 3 different notches in it. And first thing, we got to see if a probe's active. So on this particular probe, you can see, maybe you can see there's a white line that runs right down it this way. That's to indicate to you where the coil is, and it's right there. So I'm going to turn that line going downward. You see the space in here? That's to provide some spring action, so the coil will hopefully stay surface riding inside of the hole. If you use too small of a probe, or if the spring action's gone, you may have liftoff, and that's going to give you unnecessary noise, and it's also going to challenge your detection of flaws. So you want to have the right probe size, make sure that it's in nice working order. And I'm just going to tap my coil. Let me hit erase first. There we go. Oh, we got a little movement there. Obviously my probe is active, so I'm using my rotate control to set the probe motion relatively flat. I can see I'm going to have to adjust my camera mount, or you guys are going to get super annoyed with me. You got to have good quality, otherwise people won't watch, right? All right, so we're tapping away. And a good test is you always want the operating point for your material to be on the right and have liftoff vectoring to the left. So right now my coil is in air. And as I bring it down to the test material, the operating point is going to the left. So that's 180 out. So I'm going to use my angle control. I'm just going to tap, 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 like at the dentist when he's checking your filling efficacy. There you go. So that's my air operating point, and my aluminum operating point is off screen to the right. So it's vectored in the right direction, but it's way off screen. So all I have to do to remedy that is hit the null button, and that's going to bring my impedance point, my operating point for aluminum back on the screen. And now I'm just going to move past one of those flaws and see what happens. Well, I can see some flaws in there, but the gain seems to be a little bit too hot. And I noticed that my horizontal and vertical gain are not the same. So I'm going to adjust those 2 values so they're the same. So we're sort of starting with a sort of normal aspect ratio for horizontal and vertical gain. Hit the erase button. Well, could have been how I was holding my probe. My liftoff is not quite flat, so I'm just going to adjust that up a little bit again. All right, so there's my flaws. I'm going to move my operating point to the right. So I'm going to go to the display mode, screen, and like all instruments, you can adjust your null point, at least if they were made in the last 30 years, probably. Okay, so now we can see that's a good size flaw. So what do we got? We got an 8 mil deep EDM notch, gives a good signal. There's a 20 mil deep, there's a 40 mil deep. So my gain is quite hot. I'm going to bring it down a bit. I don't need to be at 80 dB. Probably maybe more like 60 some. All right, so our 8 mil deep notch is almost 2 divisions. But you can see the horizontal liftoff there, probe motion, right? Try to get that a little more exact because we like to be exact. With eddy current testing, we like to go at this with the precision of a surgeon, not a butcher. So try to get everything as set up as nicely and accurately as you can. But the phase separation angle between liftoff and our flaws could be better. Right now it's about maybe 30 degrees between liftoff and the deepest surface braking notch. But what about that little guy there from the 8 mil deep EDM notch? That could easily be misconstrued for probe wobble if you weren't paying attention, or if your test part wasn't as clean as it could be. There's a whole number of variables that could make that small EDM notch signal get washed out by the noise. So how you can remedy that is now crank up your vertical gain by itself without the horizontal gain. And what you'll see as I scan over, I'm going to scan over the shallowest notch. Right now it's what, 4 degrees? As I start to crank up my vertical gain, you're going to start to see that separation angle between liftoff and that 8 mil deep EDM notch increase. And our liftoff is still relatively flat. So now you can see you got about 80 degrees separation, and that's the shallowest flaw. There's your 20 mil and there's your 40 mil. So basically we're set up pretty well to do a bolt hole scan now. Now, I have this cool block that I bought from a guy in Great Britain. I like it because it's old. You know, I know that it's been used in the field for many, many years to perform eddy current tests, save people's lives, keep air travel safe. And it's got a bunch of holes in it. And each hole just has 100% through the depth notch. So it works well for calibrating for this. Now you got to keep in mind, the aluminum EDM block that I have and this block, although they're both aluminum, they may have some subtle differences, you know, chemistry-wise or heat treat-wise. But the noise or the probe motion may not be exactly vectored in the same manner. So how do we test that? I'm going to set this block down. And I'm just going to place the line on my probe down so the coil's facing the material. I will hit null to balance my impedance point. And when I lift off, you see how that lift-off trajectory is a bit off kilter by like 40 degrees? No problem. We're just going to rotate that down. Now, because I have substantially more vertical gain than horizontal gain, when I go to adjust the smart knob to adjust my rotation, you don't have to move it much. You don't have to move it much at all. You do have to null, though, if you want to keep your signal on the screen. Just a couple clicks will bring it flat. Okay, let's see if we're in the ballpark. Yeah, so when you adjust the vertical gain more than the horizontal gain, what it's going to do is skew your signal a little bit, and it's going to give a curvature to the liftoff line. But that's okay, just as long as you're aware that that's what's happening. Let me hit null. Null's your friend. All right, so what I'm going to do is just find a hole. Now, before we start looking at the cal block sample, it would be good to know what a hole without a flaw looks like. So you don't have to buy all your calibration standards. If you got a drill press and you got the internet, you can order a piece of aluminum cheap from Amazon and just drill some holes in it, which I did here. Obviously, there's no flaws. Unless I had a bad drill bit and I introduced some flaws into the hole, but I think they're all pretty good because I've checked them before. So all I'm doing is, and you know, when you do these bolt hole exams with a manual scanner, this shoe is adjustable. And if you read the Material Evaluation magazine from American Society for Non-Destructive Testing or other NDT trade magazines, or, you know, procedures that deal with doing bolt hole scanning, your procedure will dictate and tell you, you know, how to use this shoe. So it might say, first, set it, you know, a quarter of the depth of the probe, and then tighten your set screw. And then what you'll do is you'll insert the probe, and then you'll scan 360 back and forth. And that'll be like your first layer of the hole. And I got to keep in mind this pancake coil has a little bit of look ahead and look behind. So that may help out with the overlap a little bit. But then what you're going to do after you've done that first scan is you loosen the set screw, you put it a little deeper, you tighten the set screw, and maybe this will be the mid-depth of your hole. Put it in, do the scan, and continue on until you go through the whole depth. But today, for simplicity, we're just going to inspect the entire hole, and it's going to be about that deep. Tighten my set screw. Now I'm just going to put it down into a hole that my probe fits in. Not that one, not that one. Maybe this one here is pretty good. So now that I'm down in the hole, I'm going to hit null and erase. Now, a couple things going on here. I'm going to adjust the horizontal position more to the center of my screen there. Now, look at the trajectory of that probe motion. It's not horizontal anymore. Well, like I said, that's because our material might be slightly different. Don't fret. We're just going to go and adjust our angle to get that a little more flat. Maybe a little bit more. All right. Now that impedance point's moving around a bit, right? But you're not getting a lot of vertical deflection. You're just getting a lot of horizontal motion, right? And you're probably thinking, well, what if there's a flaw in there? I'm just not really recognizing it. Well, a good test now is to go over to your cow block that you know has a crack in it, which would be this guy. Now I'm just going to put my probe down into a hole. Gonna find the one that fits right there. This is 7/16, and I will hit null. Now you always want to null in a portion of the test material with known, good material without the flaw underneath the coil. Now I just stuck the probe in there, so the odds are I'm not on the crack because it's 360 degrees, and that crack is probably only a degree or two, right? But just to test it, we're going to rotate that probe around the circumference. Whoa, what did you see there? So now I'm just rotating it with the pancake coil on that probe head away from the part of the hole that's got the crack in it. Back and forth, a little bit of probe noise, but then when I pass that flaw, no, that's not it. That's just me manipulating the probe. Whew. You see that huge signal there? Hold on, that's not it. I'm actually pushing through the backside of the material a little bit. That's your flaw. That's your flaw. That's your flaw. You're not going to miss that, are you? Let's go to a different hole. Now this hole is a little bit bigger, but we'll see if we can see that flaw. No problem. Let's go to a bigger hole. Now keep in mind, my probe's probably not fitting that well anymore, but it's still no problem at all to find that. I'm going to go to a really big one. This one's got a lot of liftoff. And I've got the probe away from the material. And now as I rotate past it, is that it? Yeah, I mean, there's so much wiggle room in this probe. The only way that you can see the flaw is if you hold the probe up against the side of the hole that's got the crack and then rotate the probe. And there's your flaw right there. So yeah, that's just the manual bolt hole probe, and it's very effective. Now, why use manual over a scanner? Well, when you do the manual scans, you only need to buy the probe and have a tester. So, a few $100 for the probe. And it's plenty good if you're only going to be doing, a limited number of holes. But if scanning holes is part of your regular job, you're going to want to get a rotary scanner. Now, each one of the brands, may have their own tester, but they all work basically the same. So now we're going to switch our focus over to the Nortec 600 and power that baby up. Sorry for the adjustment. This is what you call logistics. What's called training logistics, right? So we've got the Nortec 600, and like most modern instruments, it's got a chip built into the scanner and the probe. So it automatically recognizes I'm using a mini-mite scanner. Yes. Probe serial numbers on there. Reflection differential. Okay. So that's going to have some self-canceling attributes to it, make our data cleaner. So I'm going to hit A for continue and then hit the little check mark. Now, this is the default screen that comes up because it already knows our application is going to be bolt hole scanning. Now, I use 240 kilohertz on the manual probe. Now, we could use 200, we could use 400. Keep in mind, there's never an exactly right frequency with eddy current testing. There's usually a most appropriate frequency surrounded by, a band of acceptable frequencies. So whether it's through a formula or the slide rule or trial and error, there's a number of frequencies that you can use that will work just fine. The only time you'd use an exact number is if you have a procedure that's well baked out and vetted and qualified. And if they say use 300 kilohertz, use 300 kilohertz because they know it works and it's been qualified and accepted by the client. But today we're going to 240 just to keep apples to apples. Now the same kind of thing. I'm going to look at my probe. And this one, does it have a line on it? The line on this one's actually up on the base of the probe. There's a little dot and there's a little red line. And you also want to line that dot and line up with the little red mark on the opening to the scanner. That way you'll align your pin receiver so you don't bend the pins. Because you know that you don't want to wreck your scanner and the probes aren't super cheap either. So keep them lined up. You might want to put a little dielectric grease on there. Because if you don't, it can be hard to pull this probe back out. So keep it nice and lubricated with some dielectric grease, and that'll extend the life of probably your scanner and your probe. So I just need to take my EDM block, and my tester's already on. Now, obviously my gain's super low because my impedance point is not moving too much. Also, it's dark in here, so I can't tell where my coil is, so I gotta rotate it manually here. Is it there? There we go. So that's going to be the side of my probe with the coil, right about there. But let's just crank some gain in here. Now, I've been playing around with my Nortec 500D this past week. And the smart knob's on the right side of the tester, which is also fine, but being right-handed, I like to handle the probe with my right hand and use the smart knob with my left hand. All right, so, we're cranking the gain up. I forgot we were doing there. So here's our gain values down here. All right, so we got some live probe action there. That's good. So now what I want to do is turn my probe on. And one of these menus, which one is it? Could it be memory? Is it main? So scan speed. I got my Nortec 600 fixed from Olympus because my probe motor controller wasn't working quite right. So they fixed it up in a jiffy and they sent it back to me. So I'm happy to have my 600 back. So all I'm doing here is I'm holding my probe horizontal to the test material. And obviously that's going to be our probe motion just rotating over the material. So going from air to the material, 750 times a minute. So that's more than, 10 times a second? It's pretty fast. Let's see. I think I had my math right. Maybe not. So we're going to go into the, let's see. It's in the dark. Give me a break. We're adjusting our probe motion to be horizontal, like that. See that? Now, there's a sweep display. That's your Lissajou display, XY, whatever you want to call it. And my gain, I don't know, maybe my gain can go down a little bit. It's in the dark. Let me see. Go down, 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 down. All right, so the same thing. We're gonna, let's see. We're gonna take our block that has holes but no flaws, and then we're just gonna find the hole that fits. This is one right here. That one's a little better. Let's see. That's a pretty nice fit. So this hole, I'm not sure, 1/4 inch maybe. But see, I could use a little more gain in there because, let's see, where's my gain button? Right there. Gain, okay. Here you can see it up here where we're adjusting it. Make our gain a little hotter. That looks good. Now here I can see my horizontal gain is higher than my vertical gain. I don't want that. So I'm gonna hit the gain, bring it down. Let's see, so 65.7 for vertical, 61.5 for horizontal. So I'm gonna leave it like that because there my vertical gain's a little bit hotter. And that's gonna give us a little more vertical when we come to a flaw. So that's right in the center of my hole with no flaw, no action on the sweep display. The only action in our Lissajou is horizontal. And then we're gonna go over to our Great Britain cow block. This probably came from Ether, who knows? Hawking. This thing's probably as old as I am, which unfortunately is getting pretty old. All right, so now here you can see a couple things going on. You can see the noise horizontal, but that big kind of C-looking thing is your flaw. Now, this is the driver pickup differential, and I believe with the Nortec 500 you don't have a figure 6 filter type. What you have is this filter 8. So what this looks like, and I'll just adjust the angle for you. Where's the angle? Right there. So if I set this filter to type 8, that kind of looks like a bobbin differential signal. You know, you got the figure 8 down and up and back to null. But a lot of people seem to prefer the figure 6, which I've come to like it quite a bit myself. So now we're just going to hit the angle button and we're going to rotate that around. Again, there's no exact phase to put that at, but you want to find a nice blend between noise and your flaw. Now what we might try here is just to crank in some more vertical gain. So there's our gain. We're gonna hit the button twice or 3 times to go to vertical gain. And we're just gonna start cranking that vertical gain up. Whoa, look at that. You're not gonna miss that, are you? Sweep display prominent. You get a huge signal there on your Lissajou. Well, let's just go back to our hole with no flaw in it, just so we can remind ourselves what a flaw-free hole looks like. And now gain's pretty hot here. But when you're rotating in there, you know, it's predominantly pretty flat. There's nothing really kicking out. And going back in the hole with the flaw, I mean, there's a very, let me see here, that one right there, very distinct signal. So you see those lights blinking on the top of my screen? That's because that box that's around the flaw on the sweep and the Lissajou, those are both alarm gates. And the only reason it's not beeping is because I don't have my horn on, because that would be annoying for you and for me. So there you have the nuts and bolts of bolt hole scanning with a manual probe and a rotating scanner. Hope you enjoyed the video.